Hello, everyone. Welcome to the online seminar on the mathematical foundations of data science. Thank you all for joining today. Our seminar is generously sponsored by 2 Sigma. It's my great honor to introduce our prestigious speaker, Professor Konstantin Karamanis. Professor Karamanis is a professor and holds the William Hartwig Fellowship in Electrical Engineering in the Department of Electrical and Computer Engineering at the University of Texas, Austin. He has made great contributions to high-dimensional statistics, optimization, and machine learning. His research interests center on decision-making in large-scale complex systems with a focus on learning and computation. Specifically, he is interested in robust and adaptable optimization, high-dimensional statistics and machine learning, and applications to large-scale networks, including social, awareness, and transportation and energy networks. He also works on applications of machine learning and optimization to computer-aided design. The title of his talk today is MLE and the EM algorithm for log-concave mixtures minimax rates. Without further ado, please join me in welcoming him.
Thanks so much, Joran, and for inviting me, and thanks to all the organizers. I'm really excited to be here today. Thanks also for allowing me to reschedule. This talk was originally scheduled for when Texas was in its deep freeze, and we had no power and no heat, so it would have been a more awkward presentation. So this is the latest results in what for me has been an area that I've been interested in for many years now, so the results that I'm going to talk about today are mostly results joint work with Zhongyao Quan, who's now a PhD student at UT Austin. But again, they have their roots, at least for me, and my own interest in them has its roots in work that I started quite some time ago. And the real reason that I find this so interesting is that we've been studying and practitioners have been using mixture models for a long time. In part, it's we're interested in understanding mixture models as a way to take advantage of building blocks and build up to more interesting models from simpler ones. And this idea has taken many different forms. This idea of so superposition is another way to think about combining simpler models, and there's been lots of work that has considered these directions. So for example, we could think about superposition of models or of different statistical structures by addition. When I'm just stylistically, I'm not actually thinking about just the sum here, but I'm thinking about x1 as representing one kind of model and x2 from another. So this is a type of problem that really captures a lot of work that's been done by many people in the community. So for example, we think about and we've modeled things like sparse, and again, when I say we, I don't mean just my group by any stretch. This is work that many people have been working on for the last decade or more. Multitask learning has been one way of modeling it, has been looking at sparse plus block sparse, 2 different structures. And this is modeled using this addition. Low rank plus sparse, for example, in robust PCA, has been modeled by the superposition or the addition of a low rank plus a sparse matrix, and so on. Various other models, low rank plus sparse plus column sparse, and so on. And one of the reasons I see for the successful treatment of these kinds of problems using tools from convex optimization is that even though the models themselves, sparsity is not a convex constraint, low rank is not a convex constraint, the superposition, this equality, y equals x1 plus x2, is a convex constraint. It's checkable by a convex constraint. If a genie gives you the solution x1 plus x2, x1 and x2, or gives you L and S, a low rank and a sparse matrix, then checking if L plus S equals the data matrix is a convex constraint. And I see that as really one of the keys to why our convex tools have carried over so successfully for solving and treating those types of problems. And we're all aware of countless results in this area that have exploited that. I'm interested in this talk in a different way to think about superposition, which is using OR. So in other words, what we see comes from one model or another model. And one reason, again, in my view, that this is so much more challenging than the superposition via addition is that this OR constraint is much harder to encode in a convex program. And so it has been more difficult to attack these kinds of problems. And so problems where their analogs are well understood and well studied in the setting where we're adding different structures have been harder to understand here. So in this talk, I'm primarily going to be interested in mixtures of Gaussians and mixtures of linear regressions. Though, as in the title in the abstract, it's really log-concavity of the distributions that I'm mixing is the key property. But also for some of the specific sample complexity and statistical rate results, I will be using further properties of Gaussians and regressions. Besides that, they're a lot easier to draw. In fact, mixture of Gaussians is the easiest for me to draw. So those are some of the reasons that I'll be focusing on these specific models. So here's a little picture just to get us started of a mixture of K Gaussians, and this is one of the main problems that I'm interested in. And mixture of K linear regressions might look something like this. I want to also point out that mixture of linear regressions, we can think about this as subspace clustering, though typically results from subspace clustering can't be applied for a mixture of linear regressions, because in linear regression, we're really considering a mixture of codimension 1 subspaces. And so it's actually in that way fundamentally different than what we typically think about when we're thinking about subspace clustering. Mixture of regressions is also intimately related to phase retrieval. So these are interesting problems in their own right, and there's still quite a bit that we don't know about them in terms of statistical limits and also algorithmic results. So two things that I'm interested in and that I'll be talking about are the setting where we have large K. So we have a mixture of many things. I'll typically think about K being on the order of the dimension. For the problems that I've mentioned, when K is significantly less, typically some form of a spectral algorithm can allow us to do a dimensionality reduction. But no, I won't be really concerning myself with that or giving a particular number for what K is, but K is scaling. I'm interested in results that are parameterized by K, and generally thinking about the setting where K is large. The number of mixtures is very large. And at the same time, I'm interested in the specific behavior, performance, and guarantees that we can give for the EM algorithm. So these on the surface appear to be two somewhat unrelated or separate questions, certainly not unrelated. The first being, what are the fundamental statistical limits for parameter recovery? So if I have a mixture of K Gaussians, how many samples do I need before I can approximate the parameters that define their means? And similarly on the statistical rate, what is the statistical rate or the minimax statistical rate there? And then at the same time, I'm interested in asking a question about the specific EM algorithm and understanding what do I need, what conditions do I need in order to guarantee that the M algorithm succeeds. And again, on the surface, these are separate questions, but actually the answer that we give to the first question, statistical limits, actually uses the EM algorithm. And so for us, the answer to both of these becomes intertwined. I mentioned I've been interested in mixtures for a long time, and I think it's worth pointing out some of their interesting properties that mixtures have compared to the what I would call the building block problem, estimating the mean of data or solving a linear regression. And this is and these different statistical results or behaviors emerge even when k is small. So this is I looked at this problem. So let's look at the simple regression problem here, just to illustrate my point here. So this is completely standard. Imagine a regression problem with Gaussian noise. We know what the least squared estimator looks like and how to compute it. We basically know everything about this problem. We know about the statistical rates of convergence when I solve the finite sample limit and want to know how. We know that the scaling of the error looks like 1 over the square root of the number of samples that I have. I think a fairly obvious point here is that as I drive up the noise, as I let sigma get larger and larger, the rate of convergence doesn't change. We still have this 1 over root n. Of course, our error gets worse. It scales. The error scales as sigma grows, but the rate remains the same. So this is something that doesn't happen. This is a phenomenon that actually doesn't happen when we have mixtures in the low SNR case. So already an indication that mixtures are somehow able to manifest some fundamentally different statistical properties. So let me just parse this. I see I've switched P for D here. So P is the dimension. So what is a reasonable notion of SNR, signal to noise ratio, when we're thinking about mixtures of regression? It might be the magnitude of the two regressors, beta 1 and beta 2, their magnitude compared to the magnitude of the noise. So that's what we're comparing. So high signal to noise ratio would mean that magnitude of beta 1 star or beta 2 star is much bigger than sigma, and conversely, the lowest in our case is when sigma is much bigger. And you can see what happens here when you look at these three terms, or in particular term A and term C. When the magnitude of beta 1 star, this norm, is much bigger than sigma, then this second term here in the min is dominated by the first term, and we see that we have the same parametric rate, sigma root dimension over n that we did before. Again, there's some log factors. This is an upper bound, so the log factors probably don't need to be there as I've written them. So I'm focusing on the other terms here. And then on the flip side, when sigma grows, is much bigger than norm of beta, then we see that the rate actually changes, and we no longer have the square root of 1 over n, but rather the fourth root. So this is results from joint work with Xinyang Yi and Yudong Chen from some time ago. But really, this was the work that really sparked my interest in this area, this joint work that we did. And kind of separately from the story I'm going to tell you today, which is for large K, I just want to mention that with Zhongyul Quan and also my colleague at UT Nat Ho, we've revisited this story and showed also that EM is able to reveal this exact statistical behavior for a mixture of two linear regressions. The work with Yudong and Xinyang from several years ago, that used a different convex optimization approach. Okay, so mixtures have different statistical behavior, or the potential to exhibit that, and that's what I'm largely interested in understanding. And the picture is in some ways pretty simple, especially for Gaussian mixtures. If we're in the very, very high SNR case, then we expect that we should really have something like this. You know, if we have a setting like what's pictured, where there's really no contamination between one cluster and another. There's no leakage, is a word that I'll use. Leakage meaning there are no points from one cluster that are closer to another. Then we really don't have a mixture problem. We just have, in this case, 4 individual problems. And so we expect that we understand, here, what would we think? We would expect in this scenario that the sample complexity is just k times the sample complexity of solving any one of the problems, and also the statistical rate should be the same, possibly up to a log factor. But when the variance starts to get larger, or actually we really, variance and separation between the means is what we're trading off. So let's leave variance, we can fix that to 1 and just think about the means getting closer. Then the picture looks a little bit different. You can see that already here, even though the centers are still, most of the points lie closer to the center from where they originated, there are some points, perhaps this point, perhaps this point, where it's not clear, and so could contaminate our calculation. And of course, as we further decrease low SNR, things become much more complicated and look fundamentally different. So, with this picture in mind, let me give a brief history of where we are when k is large. When k, the number of mixtures, is large, just for the Gaussian setting. Actually, a little bit less is known for mixtures of linear regressions. So here is my axis that parameterizes the distance between the means. Okay, so basically, as we go out to the right of the page, then the mixtures are much more separated, and then on the far left, I guess I should have put 0 here. We can also think about that problem, but this is the regime where while k is scaling the number of mixtures I have, the distance between their means is not. And for all of this, let's just think about the variance being some order 1 quantity. Let's just set it to 1. And also, I'll make this more clear later again, but all of these results are for hold when the noise is spherically symmetric. So I'm essentially thinking about, in the mixture of Gaussian setting, the setting where the covariance matrix is some multiple of the identity. I'll even be thinking about it as just being the identity, though we can, with this work, with the same kind of approach, we can also estimate what the variances are, even if they're not known beforehand. But already I find it interesting if we think about the variances being the same for all mixtures. Okay, so when we're far out to the right, we should expect results to be easy, and then get progressively harder as we move to the left. And so from about 5 and 10 years ago, there were some negative results in the setting where we have very low separation, order 1 separation. In 2010, Moitra and Valiant, and then also in very related work, Mortzhard and Eric Price in 2015, showed that in terms of sample complexity, we really can't avoid this exponential explosion in K when the separation is low, when it's in this kind of order 1 regime. And more recently, there was results that show that also the rate is going to be fundamentally different. We're not going to recover this parametric rate of 1 over root n in this regime. So these are negative results that tell us what we can't hope for. Now on the positive side, and
Jordan.
I thought I was froze. So the speaker is.
Can you send him an email? Just ask him to reconnect. Yeah.
Yeah, or you can ask him for the slides, and he can call in using a phone.
Yeah. So do you have his phone?
I don't.
And let's look at the audience attendees if he is reconnecting. Oh, he must be reconnecting. Jordan, can you send him an email asking his phone number and we can?
Oh, yeah, yes.
I think he's back.
Okay, yeah. Is that right? Yeah. Professor Caramani, you are muted.
thanks. I'm almost back. Don't know what happened. While I set up, I probably need a minute to launch this again. Any questions? Maybe if there's something that I can clarify while I'm trying to get back to the presentation. Apologies for that. Really,
No
So
problem.
far, it seems there's no questions. But
Yeah.
okay. All right, I'm almost there. Now you see my real background. This green screen was the major discovery for the online days.
So during your shooting, you use this green background, and later they add something fancier.
Yeah, I mean, well, even now you'll see it just makes the background easier to look a little more realistic. Okay, let me join Zoom. I'll quit from here and join back on my computer.
He's back.
Seems you are muted.
Okay, sorry about that. So now, so here we are. So this, okay, so these are the lower bounds, and again, what they're telling us is that what we really can't hope for in this order 1 separation. Now there were the first results for the mixture of Gaussians were actually positive results. Dasgupta in 99, and then with various follow-up works as well, showed that we can do quite well when we have this root D separation. So we need polynomial number of samples and also polynomial computational effort will allow us to estimate the parameters. So we're far out on this regime, and then at the beginning of this century in 2004, then Paul and Wang showed, again with a polynomial time algorithm and with polynomial number of samples, so efficient learnability, that we're able to get down to the k to the 1/4 separation. So as I'll show already, anything below square root of k is non-trivial. Now, much more recently, in 2017, Regev and Vijayaraghavan showed that it is possible to have polynomial learnability. So we need a polynomial number of samples to learn the parameters, all the way down to this line, so root log k separation. And they have a somewhat large polynomial, but that doesn't matter. I mean, the main breakthrough in this result is making this essentially exponential improvement from poly k to log k. And again, this is in terms of sample complexity is this result. Now, in this regime of this threshold. Oh, and I should also mention they proved that if you are below this threshold, then it is impossible to learn the parameters with a polynomial number of samples by any method. And they basically exhibit two distributions whose parameters have this required separation. Some are here, but in whose total variation distance is so small that distinguishing them to two different mixtures, that distinguishing them would require, can't be done with a polynomial number of samples. So this line here is essentially telling us, is the demarcation between what is efficiently learnable and what is not. Now I should mention that the other results that I've mentioned so far on this page are algorithmic in the sense that they also have a polynomial time algorithm, whereas these results here are not algorithmic, meaning that there is an algorithm that gives the upper bound, but that requires an initialization, which while it can be performed with a polynomial number of samples, we don't know if it's possible to do it with polynomial computation. So at this point, the initialization in this work and also in our work is basically done by brute force. Now, on the one more piece of work that's worth important to mention, and these are algorithmic results that basically give us some notion of an interpolation between this range. So a number of related works that essentially leverage sum of squares technology with that down to k to the 1 over gamma separation, so gamma would be 4 here, there is a polynomial time algorithm that requires k to the gamma computation or polynomial in that, and similarly some polynomial of k to the gamma number of samples. So that's the sample complexity and also the computational complexity. So in that sense, these results are not exactly comparable with the results of Regev and Vijayaraghavan, because in order to get down to apply these results at this threshold, we would no longer have a polynomial sample complexity. On the other hand, if you're at any k to the 1 over gamma, where gamma is order 1, then we do indeed have a polynomial time and polynomial sample algorithm. Okay, so this picture is not telling us, this picture so far is just delineating the statistical complexity of this problem. And it is not specifically mentioning anything about the EM algorithm. So one other important result, which is also quite recent, 2017, so similar time period as Regev and Vijayaraghavan and most of the other works on this page as well, shows that EM succeeds in as long as the separation is at least square root of k, the separation between the means. And again, just as a reminder to what I said before I got kicked off, we should in everything here be thinking about spherical covariance, and we can just think of variance as being equal to 1. So this is an interesting result here, and it tells us something about EM. Now this is also a local result in the sense that what this paper shows, the Yangin and Sarkar paper, shows that EM, if initialized well, and they show that you can initialize well with exponential effort. If initialized well, it will converge to it will converge and therefore recover the parameters with a polynomial number of samples, and it's just EM. So very efficient algorithm. Now this leaves quite a bit that we don't know. We don't know whether or not these polynomial number of samples that are needed in Regev and Vijayaraghavan, that polynomial in that work, again, the main breakthrough of that work was really in establishing the efficient learnability up to root log k separation. But it doesn't say anything about what the optimal sample complexity that we can hope for is, nor the rate. And it also doesn't say anything about EM. So basically the state of the art of what we know about EM is still sitting here at this root k. Okay, so the main result that I'm going to talk about in the rest of this presentation is to tell you what EM does and its sample complexity in this regime right down to root log k, which is again this threshold below which we can't hope for polynomial learnability. So here, first of all, we show that the sample complexity that first of all, I guess I should have probably reordered these. First of all, we show that EM succeeds in this regime. And what it needs to succeed is KD over epsilon squared samples. So this is telling us two things. First of all, it's telling us that the sample complexity has the right scaling. Okay, and again, I'm hiding some log factors here. The sample complexity is scaling in the right way. Basically, it's just the number of parameters divided by epsilon squared. And that is really we know that's certainly the best that we can do. And also we can see that we achieve minimax rates because we're achieving the parametric learning rate. Even if someone were to tell us the label of every single sample that we see of every single point, this point came from Gaussian 3, this point came from Gaussian 7, and so on, we would basically have these same results. Again, as I mentioned, similar to the Regev and Vijay-Raghavan work and similar to the Yan Yin and Sarkar work, these results, even though I'm talking about EM, they still require an initialization, which requires exponential effort. So no, we should really think about these as statistical results that tell us something about what are the fundamental limits on the statistical side. Now, on the algorithmic side, it tells us something about the local behavior of EM. But nevertheless, it is not proposing an efficient polynomial time algorithm. Now, again, so this is the story that I'm going to tell you today. But just as a pointer of what's left open here, I think there's quite a bit. In this picture now, we know that we need just the right number of samples, and we have minimax rate all the way down to this threshold. But for example, if we also need initialization, and we could think about these sum of squares based techniques as something that could potentially be used for initialization. But those aren't going to help us in terms of the computational complexity down to this limit. And in fact, if we are really interested in sample complexity, they're not going to help us anywhere here. Because if I have KD samples, Yan, Yin, and Sarkar tell us that that's enough to initialize if we have, and therefore we can run EM if we have this much separation. Our results say that if you have KD samples, that's enough to initialize so that EM will run. But we need exponential time. Whereas, as far as I know, if you have KD samples, if the separation is in this regime, there's not a guarantee that these sum of squares techniques will work. So I think there's quite a bit that's interesting here. We know that we have this trade-off between computation and samples. Anyway, that's not what I'll talk about today. Though I think these are interesting things that remain to be resolved. So this is a story that I'm going to tell you today. Okay, so I want to say a few specific things about the mixture model and the EM algorithm, and then I'll talk about the conditions for EM's success. Okay, so just to finally state the specific model that I have in mind, I'm thinking about a mixture of k distributions. So pi k here. These are the mixing weights. I should mention that I've presented this as I need KD samples. I said, of course, we should expect that k is not the real value. It's more like 1 over the smallest mixing weight here, and that's again unavoidable. If you have one mixture that has very, very, very little weight, you need to wait around to get d over epsilon squared samples from that mixture, no matter what. Even if you so really it's not k, but it's 1 over pi min. But again, for the purpose of this talk, I'm just going to assume that this is a balanced problem, so that the pi's are all just 1 over k. Again, that's not material to our results. We can in fact estimate the pi's as well, but just since I wrote pi k's here, I want to make sure I explain how that relates to the bounds that I give. Now, our goal is to estimate the centers, the theta k's. And again, we can also estimate the pi's. In fact, we can also estimate the variances if they have different variances. I guess in this case, I'm not talking. P is just my log-concave model. Okay, so the two problems that I'm specifically interested in are that of spherical Gaussians. In that case, the distribution, this is the log of the distribution, and also the mixture of linear regressions. And again, in that case, this is what f looks like. So a natural thing to think about is the max likelihood estimate, and to try to understand when this gives some results. So it's, again, pretty recent work has shown that if we have two components, then the landscape of the likelihood is quite favorable. In particular, in 2017, Daskalakis, Zamos, and Zabetakis showed that for Gaussian mixture of two components, we can initialize randomly, and will converge with probability 1. Again, with Jonyol and some other co-authors, we showed that something very similar happens for a mixture of linear regressions. But this is not something that we can count on for anything more than 2. And in fact, in 2016, Jin, Zhang, Balakrishnan, Wainwright, and Jordan showed that we have non-spurious local minima of the log likelihood function whenever we have more than 3 components. So, in particular, they showed that random initialization and then running EM or running gradient EM would basically take exponential effort in order to minimize it. So we really can't expect that any of these algorithms are going to do well without initialization. Okay, so now I'm thinking about this setting here where I have, for Gaussian mixtures, root log k separation. So where does that come from, and how should we think about it? So the same way that for Gaussian mixtures, I showed that that axis, that horizontal axis, that parameterized difficulty, in a more general problem of mixtures, difficulty is parameterized by how likely we are to think that a particular point that we see came from mixture I when it really came from mixture K. And so this is what this is saying here. For mixtures of Gaussians, this is entirely determined by the separation of the means, again, because we're thinking about a spherical setting. And therefore, this quantity here, which we can, again, think of more generally, translates into this requirement for us for mixture of Gaussians of a separation between the means. For a mixture of regressions, this is, again, determined in the same way by the mixture of the means. And for mixture of linear regressions, we're going to assume that we're in this regime where the separation scales with K. Now, I'll come back and mention this at the end. We think that this is the right number, but unlike with mixture of Gaussians, where we know that root log K is this threshold between polynomial efficient learnability and not quite sure for mixture of linear regressions, though that would be my guess, and we can discuss that later. A very brief refresher of what EM does. Essentially, it alternates between 2 steps: guessing the labels and then updating the likelihood estimate, and then updating the M step, which updates the parameter that maximizes now the likelihood estimate, which is now concave once I've fixed these weights. So this is what EM is doing. For those of you that don't think about EM a lot, we're really the key point is in remembering that this M step is essentially requires the solution of a convex optimization problem, because our distributions are log-concave by assumption. So we could think of more general mixtures, but this is where that comes in for us. So the first result that I find exciting, though it really is, at the end of the day, just an observation, but it was something that I didn't realize, is that the sufficient conditions that we use that guarantee that EM converges locally also guarantee that the log likelihood function is locally strongly concave. So that means that even though we set out to analyze EM, actually we're analyzing all of we're also analyzing any approach, any local approach, gradient EM or even just gradient descent on the log likelihood function, which again overall is non-concave and has spurious local minima. I should mention that these are not equivalent results. So with some other methods, we can show that EM converges in a larger basin of attraction, but the results I'll present today are really showing that in the region where sufficient conditions that guarantee one also guarantee the other. So there's a lot of notation here, but I'll try not to show too much of it. But some things to keep in mind are, again, what these, I'm going to use WIs to be the mixing weights. I think at some level these are pretty standard notations, and essentially it's just a balance of the likelihoods of the a posteriori likelihoods once we've calculated a particular solution. And then what I've written here, especially in the last two lines, or just to highlight one of them, this is what the Hessian of the log likelihood function looks like. So we should expect to see things that on the diagonal that look like weights times the Hessian of the individual f of a particular distribution I, and then in the off diagonal we'll have these other blocks that combine the gradient of f for model I and the gradient of the likelihood for model J. So these are the components that we want to show of the likelihood that show that we have that make up the Hessian. Okay, now let's try to see how we're going to link this to EM. So there are some details to fill in here, but some work, maybe some of the earlier work that gave finite sample guarantees for EM, basically honed in on this quantity, which initially was called gradient stability, which basically controls this the gradient of the Q function at theta and at theta star. And essentially, this result by Balakrishnan and Wainwright and Yu showed that as long as this is controlled by the difference between theta and theta star, so as long as we have this like Lipschitz-like continuity of the gradient of Q, then we can essentially follow the standard proofs of linear convergence for gradient descent for smooth and strongly convex functions, more or less, and get the result that gradient EM and also EM converges. So I'm not going to go into the details of that portion here, but I just want to mention that we understand well what it means for the likelihood to be locally concave. That just means that this Hessian that built out of these things, out of these blocks here, is itself concave. But the key for EM to converge is the control of this quantity. And the reason that this, again, a lot of notation here, but all I just want to point out is, again, if we write out what this difference is, what the gradient of a Q function at theta and theta star looks like, then we see that we basically have these two derivatives of these two gradients of f at and the m step at model I and at model J. This U here, I've just used the intermediate value theorem. So this is this U. We can talk about details after the talk or offline. I'm happy to talk at any point. But what I'm really mainly wanting to point out is this really simple observation that if we write it down in the right way, this property that we need for EM to converge pops out the same quantities as what makes up the Hessian. And so what I'm calling here H dash are the quantities related to EM, and H is what the quantities related to the likelihood. And so we can show that these are very, very close. And essentially what this means is that what we need to guarantee linear convergence of EM is essentially the same conditions that we need that are sufficient for guaranteeing that the likelihood is itself concave. And this is basically this picture. And the way that these sufficient conditions work is actually sounds very coarse, but it's enough for us to obtain the information theoretic limit for sample complexity and also minimax rates. And it basically is just a diagonal dominance condition. So we really, the conditions that we ask for are conditions to guarantee that each one of these blocks is strictly negative definite, and each off diagonal block is small enough. And so we have this diagonal dominance showing that the log likelihood is concave locally. And those are, again, exactly the same conditions that can be used to show that this critical quantity here that we need for convergence of EM also holds. So this is the first part of the conceptual story. So now a little bit more of where this comes from. Again, with any mixture problem, we need to control the leakage. This is really the only problem. If we knew the samples, if we knew the labels of each sample, then we don't have an interesting or challenging problem. If I know that this particular point came from this mixture, then I just have a decoupled problem. So this is really the picture that we need to have in mind. This is the kind of thing that we need to control. Good events are when points somehow are easy to identify. We know that this point came from this center, and this is a bad event because it's not clear. I see this point, I might ascribe it to the ith center instead of the kth center. So let's think about a first try. If we know that that the fundamental problem in mixtures is to control this, what do we need? How could we do it? So first try is to say, well, I know I'm in d dimensions. And again, my picture here is for Gaussian mixtures, but it applies similarly to linear regression and so on. It's just easier to draw and think about. Okay, so how could I preclude these bad events from happening? Well, the first try is, let's just say, I'm in the spherically symmetric setting, so let's just make sure that the norm of the noise is smaller than the distance between my centers. Oops, I see I switched to mu's here. Apologies for that. So these are mu's and thetas are the same. Okay, so I'm in d dimensions, variance is 1 in every direction, so the noise is going to be in this shell. That's going to be radius squared d, and we know that we have a very sharp concentration of what a Gaussian in d dimension looks like. So if I just ask for mu I minus mu j to be bigger than that, then I'm in business. So more or less, this would be our first step that would get us towards a result that says that the log likelihood is concave locally if I have this much separation, or that EM converges if I have this much separation. So that's where that comes from. But we want to do better than that. We don't want root d. And so we see that there's actually a lot of room to do better if we're a little bit more careful at thinking about what these bad events look like. So rather than saying that they don't happen or controlling the probability that they happen in this way, we could take a little bit of a more delicate approach and look at something like this. So here's what I've tried. I did my best to illustrate. So what is it that we really don't want? I don't want a sample to come from the kth center and somehow fall in this direction. Do I mind if it's way out here and it has a big variance, it comes at a distance that's much bigger than the separation? Of course not, if it's in this direction. So what I really want is to rule out this sliver. I don't need to rule out, I don't need to do what was in the previous slide. What is another bad event that could happen if I'm trying to estimate theta star k, theta k star, and my current estimate is theta hat k? Well, I also don't want samples to fall in the direction that would make me, that would fall in this direction of the mistake that I've made in estimating. But again, this is now just a small little cone that has exponentially small probability under the Gaussian distribution. Similarly, this cone has exponentially small probability under the Gaussian distribution. And that's exactly the calculation, basically in words. So what happens here is that this probability of error that we get, this probability of these bad events, is going to be very small. These bad events are going to be very rare. Just they're essentially going to be controlled by the probability of a Gaussian in these little cones, which is going to scale like e to the minus theta I minus theta k squared. And so you can basically see from here. Of course, it takes some calculation, but you can see. I mean, and there are details. But this is where this root log k is coming from, compared to the root k. So it's really in terms of more careful geometric analysis and exploiting the property of high dimensional Gaussians, where these results come from. Now, how about sample complexity here? So where does this come from? And so for sample complexity analysis, these events and defining these events is also the critical idea, and it's critical for obtaining the right bounds. Now, I've also mentioned here initialization requirements, and what I mean here, the reason that we need initialization requirements is that so far I'm just talking about the local convergence of EM, or the local concavity of the likelihood function. But that's by itself not enough to tell us about the sample complexity of this overall problem. So one difference between our work and prior work, and really this was one of the main reasons that we were able to get the information theoretic sample complexity compared to just polynomial sample complexity, is that it comes down to initialization requirements. So our analysis, which essentially is a picture that I just drew, that's the idea. That analysis not only improves root k to root log k for EM, but also the basin of attraction is large enough so that we can initialize with KD samples. The basin of attraction that was used for in Regev and Vijay-Raghavan, for example, needed more samples, even initialization. So this is why the initialization is really the key to go from these results of local convergence of EM or local log concavity to sample complexity bounds. So in a nutshell, these are our sample complexity results. So I see it's 11:01 right now in my time. Maybe I could have a few more minutes. How does it? What do you think, Joran?
Sure.
Okay. There's one other technical idea that I just want to share in addition to finally just saying what the results are. So our results basically say that as long as we have this many samples, which is again KD. So that's what this essentially looks like. Remember, pi min, you can't avoid that if you have one mixture, one element of the mixture that's very, very rare. But if all of the mixtures are equally represented, then this looks like KD. Now this is saying as long as you have KD samples, then you're in this regime where your log likelihood is locally concave, which means that you're going to converge to the minimizer of the log likelihood. And EM also is going to work in that regime. So what's left? What's left is to understand how far is theta. So far we know that EM converges to theta n star, but how fast does theta n converge to theta star? And this is the question of statistical rate. So I want to mention this because we get minimax rates, but there's one other interesting technical idea, I think, if I may say so, that I want to share before I quit. So first of all, how do we get the statistical rate? One way to get the statistical rate for this problem is to start at the optimal solution, theta star. This is the population optimal solution, and apply one step of finite sample EM. We know that we're going to move away from that. And how far we move away is exactly going to help us control the statistical rate. And this is basically what this says here. So this is the distance between theta star n and theta star. This is what we want to control. And just by triangle inequality, we get that that theta star n, the difference between theta star n and theta star, is controlled exactly by if we call that epsilon n, that's controlled by how far away finite sample mn, the finite sample EM operator, moves us away from the population solution. Okay, so this is just simple triangle inequality. So let's write this down. Let's write this distance between the theta star and where one step of finite sample EM takes us. So this is, if we write it out, it's going to have terms that essentially look like this for Gaussian mixtures, and there's something similar for linear regression. So let's ask, how do we bound this? Because this is what I want to do. This distance here is exactly what controls, is that epsilon n in the previous slide. That's what controls my statistical rate. Now I could just say, well, I'm in business, I've assumed everything inside is Gaussian, so everything is good, and I could just try to bound this using Gaussian concentration or sub-Gaussian concentration. But that's not going to be very good, because you can see that these terms here could be quite big. If xi didn't come from theta 1, then I'm going to have terms that look like root log k, which is no good. So we need a different idea, and I'll just mention this in one word here, which is this is a tool that we found really useful, and conceptually it's very simple, but it really gave us the edge compared to all the previous work that we were aware of. And in words, it's very easy to state. It basically says you want to control something like deviations from a mean. Well, or you want to control some of a random variable. What you can do is think about a glorified union bound in the following way. We think about events A1 to AM that are disjoint and partition the space. So the disjoint and their union is everything. And then we balance how bad it is when x falls, how bad it is for our concentration when x falls in one of these events, say A2, versus how often that happens. And balancing those two is, again, essentially the spirit of this entire work, or at least our technical angle in this work, which is balancing the impact of a bad sample on our estimate versus how likely it is for such a bad sample to occur. And that is essentially the story here. So this is a result that basically says that what you want to control, the concentration to the mean that you want, to the population calculation that you want, can be controlled by this product of how bad it is, how far off it is, versus how likely it is to happen. And so doing this carefully for this problem basically shows that when n is big, in other words, when an event is very likely to happen, it has to be a good event, which means that the impact on our calculation is going to be very small. A simple idea, but this was really the kind of core technical nugget in both our work for linear regression and for mixtures of Gaussians. So as a summary, we show that for Gaussian mixtures, we get this root log k with information theoretic optimal number of samples and also the minimax rate. And for mixed regression, this similar results hold. We get the minimax rate. We require order k separation, which again is my best guess as to what is the threshold, but we don't have a proof of that. And in parallel, essentially for free, we also get that the likelihood is concave, which means that you don't have to use EM. You could use any first order algorithm that you like. I think I mentioned along the way that we know a few more things. We know we can also estimate the variance parameters with really no material change in the results. We can also estimate the mixture parameters, those weights. What we don't know is how to deal with unknown covariance matrices that aren't spherical. We've confessed we've thought about this quite a bit, but we don't know what to do, even though EM seems to continue to work. So it's intriguing here, but clearly that's a harder problem. As I also mentioned, I think that there are some really intriguing algorithmic questions left open here surrounding initialization, especially when you're at this KD number of samples. Even at much bigger separation than root log k, we don't know what to do there if you have that number of samples. Whereas if you're given polynomial number of samples, we know, thanks to those works I mentioned that use sum of squares, that we're back in business. In conclusion, I'll just say that I think mixtures are a fascinating problem because they really exhibit, or they can exhibit, some very interesting statistical properties. And these days we're looking at some dynamic problems. And I'm always happy for any discussion that anyone has. So thanks for your attention. And if there are any questions, I'll be happy to answer them if time permits.
Thank you, Professor Caramani, for the great talk. And as for the questions, the first one is, could you please elaborate more on the initialization part? So how the parameters initialized, and it seems it's computationally intractable algorithm.
Yeah. Okay. Absolutely. Yeah, it's important to be clear on this. So maybe I'll just go back to this slide here, so we helps to talk about it. So now for our results, just like Regev and Vijay-Raghavan results, in order to initialize, we use brute force exponential time search. So we basically just look at an epsilon net. And we initialize in that way, and that takes exponential time. And one difference that I want to mention again is with respect to this work is that because we have a slightly larger basin of attraction, we can initialize with KD samples instead of polynomial KD samples. But in either case, we need exponential effort. Now, what happens in? Yeah, so that's my short answer there. Now these results. Oh, and I should mention that the result by Yen and Sarkar that EM converges at this separation also requires exponential effort to initialize. This is a result that requires polynomial number of samples and polynomial computation. So basically, until the work by Diakonikolas, Kane, and Stewart, Hopkins, Lee, Kotari, Steinhardt, and Struer just a few years ago, this is essentially the state of the art in terms of what we can do with polynomial computation. Now, this work essentially gives us a lot of information about what happens here, but you can see that as soon as we're interested in something that looks like log k, gamma is no longer can be considered an order 1 quantity. So again, two things that I think are interesting. First, first of all, these results here do not tell us that we get polynomial time initialization down here. But also, this is not just the computational complexity, but also the sample complexity. So we actually don't, even in some regime here, we don't know how, or even at k to the 1/4, as far as I know, I don't know how to initialize even out here with a linear number of samples. So if I give you KD samples, I know that the problem here is solvable. I know that the problem all the way down to here is solvable from a statistical perspective, but I don't know what to do that I don't know how I could do that with polynomial computation. Whereas if you give me more samples here, if you give me k to the 4th samples, then I could apply, one of these results. So I think these are really interesting.
Yeah, yes, this gap between statistics and computation is really interesting.
Yeah, exactly, as you know, yeah.
Yes, and another question is about whether it's possible to extend to other settings. For example, the setting where the number of clusters is unknown to us, and perhaps we will use a EM algorithm with over-parameterize the EM algorithm in the sense that the number of clusters specified is larger than the underlying problem.
I think that's another very great question. It's when we have a very high separation, the over-parameterization is not that much of a problem. But as the separation decreases, over-parameterization is a problem and can change the statistical behavior of an algorithm like EM. I'm not sure exactly what happens here, but I think that is definitely a critical question. I think it's a very good question.
Thank you. And maybe the last question is: have you thought about maybe mixture of Gaussian or mixture models with multiple clusters and also sparsity? Then there seems to be 2 degrees of freedom. One is number of clusters and second one is sparsity. Then have you thought about the computational and statistical trade-off involving these 2 dimensions? Are there any works doing that?
That's a good question. I mean, I guess there we want to change D to be, something like sparsity log D or so that's a natural thought. Let me see. I mean, I'm thinking about how that impact, especially if we want to be in this regime where we know we need this very good initialization. The initialization, I think it's, I guess I'm thinking online now, so my short answer is I don't know, but I think it is interesting because the quality of the initialization that we need is inversely proportional to K. And so, there's nothing you can do about that in our setting, but when you have sparsity, obviously, if you're very well initialized, extremely well initialized, then sparsity is no longer, you may actually have you may actually know the support in that setting. So I can see that there is a trade-off there between, and especially what models of sparsity, are you using a hard model of sparsity or something else? I think it's interesting. I don't have much concrete to say there.
Thank you. Yeah, thank you. And also, that's all the questions I have. And thank you again for the great talk.
Great. Well, thanks very much. I really appreciate it.
Thank you. And also, we would like to thank the audience for attending. And see you next week. Thank you. Take care.
Bye, everyone.